This is AP Calculus 5-8, sketching graphs of functions and their derivatives. What we're going to do in this section is put a lot of stuff together that we've talked about and talk about how f prime, and f double prime look as graphs, how those things affect what your f graph looks like. And then in the next section, we're going to go through and start comparing your f graph with your f prime graph and your f double prime graph, and just make a bunch of connections between those three derivatives. The main thing you need to understand for this section is how f prime and f double prime affect your f graph, your function. So we're just going to review some things first, and then we'll get into the graphing. If f prime is greater than 0 or positive, so if the derivative is positive, that means that the slope of f, your graph of f, is going to be positive, and when the slope is positive, f is increasing on that particular interval. If f prime is less than 0 or negative, that means that the slope is negative, and that means that the function is decreasing within that interval. If f prime is equal to 0, then you have a horizontal tangent line at that spot on your graph, and most likely that is a maximum or a minimum. It will be a maximum if it goes from increasing to decreasing. It will be a minimum if f prime goes from decreasing to increasing. If f prime does not exist, then that means you have one of several things. You might have a vertical tangent line, you might have a hole in the graph, you might have a vertical asymptote, and I left one off, you might have a sharp turn. So if f prime does not exist, there are several things that happen. And if your directions are to graph f and f prime doesn't exist, then you would be able to choose which one of these you want to use depending on the other information. Sometimes you might have more than one correct answer when f prime doesn't exist. If f double prime is greater than 0, now remember f double prime, the second derivative, tests for concavity. Okay, f prime tests for the slope of the tangent line, or whether it's increasing or decreasing. F double prime we get that for concavity. So if a function is concave up, f double prime is positive or greater than 0. So if f double prime is greater than 0, that means the function is concave up on that interval, and the slopes are increasing when something is concave up. Now let's think about that. If something is concave up, I'll just do a little picture right here. Think about the slopes of that concave up graph. The slopes on this side are negative, and then they gradually become 0, and then they gradually become more and more positive. So they're going from negatives to positives, so our slopes are increasing when we have a f double prime that is concave up, okay, or an f double prime that is positive. If f double prime is less than 0 or negative, then that function is concave down on that interval. And if an interval is concave down, if you think about that, aren't the slopes decreasing? They start out positive on the left-hand side, go to 0, and then go to a negative. So the slopes are decreasing if it's concave down. That will become significant as you're trying to analyze tables that you've been given. They're going to give you tables, and they're going to ask you to take the information from the table based on your f prime and your f double prime information and draw the graph of f using that information. So you need to understand that if something is concave up, then the slopes are increasing. If something is concave down, the slopes are decreasing. Here is the first example that we're going to do. I have a chart here, and my chart, I have intervals, like this first interval goes from negative infinity to 3. Then we're talking about what happens at 3. This interval is from 3 to 5. Then we're talking about what happens at 5. This interval is from 5 to 7. We talk about what happens at 7, and then this interval is from 7 to infinity. So my domain of this function goes from negative infinity to infinity, or all real numbers. And then I've given you some information about the intervals and about those particular x values for f prime, and f double prime. So remember, f is talking about the initial or the original function. So if f If it has a positive, that means f is above the x-axis. This f, that means that it's 3. When x is 3, f is 1, y is 1. So that's the ordered pair 3, 1. So we know the ordered pair 3, 1 is on the graph. And so on. So this plus means it's above the x-axis. 2 means we have the point 5.2. This x means it's above the x-axis. 7, 3 is an ordered pair, and this means it's above the x-axis. So based on this information, this entire graph is above the x-axis. So when I drew my coordinate system, I just drew a positive x. I did the x-axis, and then I am talking about stuff above the x-axis based on what they've given me here. And my significant ordered pairs that they gave me were 3, 1, 5, 2, and 7, 3. So I just made it the positive quadrant. And we're going to graph this based on the information in the chart. Remember, f prime represents slope of the tangent line, and f double prime represents your concavity for the function. So I'm going to let you pause the video, get all this information down, draw your graph, and then I'll walk you through how we would do this problem. Okay, so the first thing I'm going to deal with is my f function, this information here. And particularly, I'm going to find the ordered pairs that they gave me. That's the easiest thing to do. You'll have some concrete ordered pairs to put on your graph that you can base everything else off of. We know, based on this information, that this right here represents the ordered pair 3, 1. So I know the ordered pair 3, 1 is on my graph. I know 5, 2 is also on my graph. And I know that 7, 3 is on my graph. 7, 3 is right here. So it appears that my graph is continually increasing. Okay? To determine if that's the truth, we'll have to look and see what the rest of the information is telling us. Now remember, if a graph is continually increasing on its entire domain or continually decreasing on its entire domain, what is that called? It's called strictly monotonic. Okay? So if it's only increasing or only decreasing, that's called a strictly monotonic function. All right, so I have graphed the 3 ordered pairs. I know that all of this, what we've got here, everything is for my f function is above the x-axis because those are all positives. So I'm okay to assume that everything is going to be above the x-axis for my graph. It's not going to go below the x-axis because the entire domain is accounted for here. This goes from negative infinity to 3. This goes from 3 to 5, from 5 to 7, and then from 7 to infinity. So the entire domain is above the x-axis. That's what we can get out of the f line. Okay? 3 ordered pairs, and everything is above the x-axis. Let's move to f prime. Okay? We know that in this interval right here, the slopes of my function are negative. Now, think about the slope being negative. It's this direction. Okay, if my slope is negative, then that means this one is not going to be strictly monotonic because we have a negative slope here. It's going to go from a negative slope to a positive slope. Okay, so to the left of this ordered pair, we're going to have a negative slope. To the right of that ordered pair, we have a positive slope. Now, think about your first derivative test. If something goes from a negative slope to a positive slope, okay, negative to a positive, didn't we say we had a minimum where that happens? So that means we're going to have a minimum at 3, 1. I have a negative slope up and a positive slope going up in that direction. We know we have a minimum at 0. Now, I can't draw everything in between until I talk about the f double prime. But I'm going to continue with my f prime graph first. At 5, 1, 5, 1, I have a positive slope to the left, so a positive slope to the left, right? This would be a negative slope, so I have a positive slope to the left, so it's a positive slope here. and to the right of the 0.51, I still have a positive slope. So it's not going to go down, right? Those don't change directions. It's still going to be a positive slope direction. So it's still a positive slope direction there. And then from the 0.73, to the left of 7.3, I have a positive slope. Look at that, positive slope. To the right of 7.3, I have a positive slope as well. Okay, so it looks like I might have some changes in concavity or some points of inflection here that I need to talk about. So let's look at F double prime and see if we can put all this together based on what F double prime says. F double prime on the interval -∞ to 3 is positive. So it's concave up from -∞ to 3. Well, that makes sense. That's concave up. It's also concave up from the interval 3 to 5. So it's concave up for this entire interval from 3 to 5. So now, look at what I've got here. I've made this positive slope look this direction, but if you think about that, if this entire interval is concave up from -∞ all the way up to 5, wouldn't that mean this entire function, we know that's a minimum, the entire function is concave up like that. Concave up. Okay, so me having it this way, that meant it was concave down. It needs to be concave up based on what it's got there. Okay. If you look at the interval from 5 to 7, okay, 5 to 7, it says that that is concave down. Okay, now think about that. That looks like concave up. That looks like it's concave down. So if it's concave down and my slope has to be positive, it's going to look like that. It's concave down with a positive slope. And then I'm going to look at 7 to infinity. It's concave up with a positive slope. Concave up with a positive slope is going to be that direction. So there is a good rough estimate of what my graph looks like. Now, let's talk about these ordered pairs right here. If you think about what's happening from 5.2 to 7.3, at 5.2, it tells us the slope is 1, which that's not anything we can really draw exact at this point. If they wanted us to draw the F prime graph, then that would be significant. We could use that. But they just are asking us to draw the F graph. So look at F double prime on the interval 3 to 5, and then again on the interval from 5 to 7. Notice it changes from concave up to concave down. And remember, we learned when we were talking about concavity that if concavity changes from positive to negative or negative to positive, we have a point of inflection there. So that means at 5.2, at that ordered pair, there's a point of inflection. And you can see it changes from concave up to concave down. And that would be a point of inflection. That happens again at the ordered pair 7.3 because it changes from negative to positive. F double prime changes from concave down to concave up. And that would be then another point of inflection there. Notice where we have points of inflection, F double prime is 0. Okay, that's important to understand. Where we have points of inflection, F double prime at that ordered pair will be 0. So here's the next example. Go ahead and copy the information down. It says F is continuous and twice differentiable. Sketch the graph of F given F of -2 is equal to 10, F of 0 equals -5, and F of 2 equals -20. This one takes the ordered pairs out and just gives me F prime and F double prime. So this is just another way of presenting kind of the same type of problem. So when I drew my graph, I drew it to make sure that those ordered pairs would fit on my graph. And then I've got the intervals. This time the intervals are written in set notation. So I've got from -∞ to -2. What happens at x equals 2? From -2 to 0. What happens at x equals 0? The interval from 0 to 2. What happens at x equals 2? The interval from 2 to infinity. okay? And then I give you f prime and f double prime for all of those intervals or all of those ordered pairs. So go ahead and pause the video, copy that down, and then we'll get started on doing the work. Okay, so again, the first thing I'm going to do is I'm going to graph these ordered pairs that they gave, because that's the easiest thing to do. So negative 2, 10 is right there. F of 0 is negative 5. And f of 2 is at negative 20. And then we're going to use the information from the graph to decide what's happening and how the graph goes through these ordered pairs. F prime on the interval negative infinity to negative 2, so to the left of negative 2. F prime is positive. It has a positive slope, so positive slope, but it's concave down, meaning concave down, like that, okay? So if it's concave down with a positive slope, that means to the left of negative 2, it's going to be looking like this side of a curve, okay? Look at what happens at negative 2. The slope at negative 2 is 0, so that tells us there's a horizontal tangent line there. It is concave down because f double prime is at negative 2. Now think about the second derivative test that we learned in the last section. In the second derivative test, we said that if we have an ordered pair where f double prime is negative, that is a relative maximum. So we know we have a maximum at x equals negative 2. Look at what happens to the right of 2. It's still concave down, but this time the slope is negative. Well, that makes sense. Concave down, slope is negative, would be the other side of that curve. So we know that it's going down in that direction on that side. Okay, now we have to talk about what happens at x equals 0. At x equals 0, we know there's a negative slope. It's not 0 this time, right? The slope is negative. So it's not going to be a maximum or minimum, but the slope is negative, okay? It tells us that at x equals 0, f double prime is 0. Now, what did we talk about in the last example? If f double prime is 0, that's where we have a point of inflection, okay? So we know this is a point of inflection. That means that's where it changes from concave down to concave up. Let's see if that's true, okay? At x equals 0, point of inflection, we think. The interval from negative 2 to 0 is concave down. The interval from 0 to 2 is concave up. So yes, in fact, that is a point of inflection. So this curve goes down, and it's concave down until we get to that point. And then on the other side of that point, it starts to be concave up. When we get to this point, x equals 2, the slope is 0. Well, the slope goes from being a negative to being a positive on the other side of that. So that means at x equals 2, that would be a minimum because of the slopes, but it's also a minimum because of the second derivative test. F double prime at 2 is positive, meaning that's a local minimum. So that's our minimum. So at the other side, on the other side, it's going to be going up. This would be a good rough sketch of the graph that they've described in that table. So here's another type of example that they're going to ask us to be able to do with these type of problems. It says given f, a twice differentiable function. Okay, so they give us f with a domain of negative 4 to 4. So they've given us a portion of this graph just with the domain from negative 4 to 4, and they want us to analyze this graph based on what is being done here. Now, notice this is function f. It's not f prime, it's not f double prime, it is f, okay? The domain is negative 4 to 4. The point of inflection happens at x equals 3, so that's going from concave up to concave down. And then they want us to state what can be said about f of 2, f prime of 2, and f double prime of 2. Okay, well, let's think about that. F of 2. Well, we don't know. We know this is where f of 2 is, right? But do we know what f of 2 is equal to? We do not. We know that it's below the x-axis. So we know f of 2 has to be negative, okay? So we know f of 2 is less than 0, okay? So it's negative. What do we know about f prime of 2? Well, if you look at f of 2, it looks to me like that's a horizontal tangent line, okay? So we know that f prime of 2 is equal to 0. And look at f double prime of 2. Well, f double prime tells us whether it's concave up or concave down. That's obviously concave up. So f double prime of 2 is greater than 0. It's positive because it's concave up. And what they're asking us to do here is to compare these three things. Well, if f of 2 is negative, wouldn't f of 2 be less than f prime of 2, which is 0? And that's less than f double prime of 2, which is greater than 0? So they are just wanting us to compare these three things based on what their signs are, okay? So that's all there is to that one. We're just comparing based on whether f is above or below the x-axis. That'll tell us whether it's positive or negative. Or if it touches the x-axis, we know it's at 0. If f prime, if we look at it, this one happened to be 0, but f prime could be positive, it could be negative, depending on what the slope is doing at that point. And f double prime is concavity. It's obviously concave up at that point, so we know f double prime is positive. Okay, here's another example of what they might ask us to do in this section. Here they've said that they've given us f prime. So this is a graph of f prime. This is a graph of the derivatives of the f function, okay? And it says to determine when the graph is concave up. You have to think back to what we talked about at the beginning of this section. Didn't we say that if f double prime is greater than 0, that means the graph is concave up? Okay, we wrote that down at the beginning of this section, okay? Well, and then we went on to say that if f double prime is greater than 0 or positive, it's concave up, which also means f prime, or the slopes, are increasing. And we said that if f double prime is less than 0, it's concave down and the slopes are decreasing. Okay, now think about this. If this is f prime, and we know that f double prime is concave up when f double prime is greater than 0, and that happens when it's concave up, and it's concave up when f prime is increasing, aren't they just asking us to look at this f prime graph and tell them when this function is increasing? Okay, this function is increasing on the interval -1 to 2. So that's where f would be concave up. It's concave up when f prime is increasing. And that happens from -1 to 2. So it's concave up on the interval -1 to 2, because that's where f prime is increasing. Okay, the function is increasing. Now, what if they said, when is it concave down? Well, this function is concave down anytime f prime is decreasing, going in a downward direction. So now it looks to me like it keeps going forever in that direction. So it's concave down. It'll be decreasing from -infinity until we get to -1. And then it's again decreasing from 2 to infinity. So that one has two places that it's concave down because f prime is decreasing in those two intervals. Okay, so you have to distinguish between whether they've given you the graph of f prime, or f double prime. We'll deal with more f double prime graphs later. But for now, we're just going to be dealing with f graphs and f prime graphs, and then some tables to draw the graphs from the tables.